Good afternoon, everyone. My name is Zazi, and I'm from Dalhousie University. Thank you very much for having me to present my topic. So my topic for today's presentation is skill-based explorative views, a selection method for mobile devices. This is just basic outline. I'll start with introduction, then I'll talk a little bit about the technique itself, then user study, and conclusion at the end. So my research is mainly focused on 3D models on mobile devices. And 3D model has been used for quite decades, and mechanics and engineers, they design, repair, or maintain like complex machinery with the help of 3D digital models. And as a digital assistant becomes more important as the model becomes more complex. Thus, the improvement to the process of understanding the internal structure of 3D model is very important. And our main goal is, because our research is sort of a Boeing mobile project, so one of the problems they have is that since how to like efficiently fix some small and very occluded part which is not accessible by visual. So the problem is how to select small and occluded objects on mobile devices. I know like there are a lot of methods that have been accomplished on a desktop, but what we want to really focus on the mobile devices because like some planes, they're really high. So like if you want to go top, it's not very convenient to bring the laptop. For part selection method on 3D model, there are a couple of methods. For example, text-based. For example, if for the application you enter the name of the part you want to search in a 3D model, then it will come up. The problem to this method is that like typical plane like Boeing 747 contains like millions of individual parts. So it's really hard to remember each of name. And of course, the name is really long. There are also contextual-based method like ghost wheel here. So like this is sort of X-ray, so you can see the internal part. But the problem is you don't really have access to the certain parts. I mean, it helps you to comprehend the structure, but that's not what we're looking for. So then we want to explore more of the explorative views. Explorative views have been around for quite a long time, and like most important, one of the research is interactive exploded diagram by Agrawala, and the problem of this method is it's implemented on a desktop, but it has computational expenses. What it does, it calculates. It computes a relationship between each each model, its position, and its relationship between each other, and then it sort of follow the law of physics, like what is means you can't really pass through each object, like like Superman. So and another one is compact explosion, but this one is more focused on the repair parts. And here, the name of our approach, we call it skill-based explosion technique. This is the prototype we developed for our research. So mainly there are three parts. On the left side, it's very basic interaction command or a GUI, and on the middle is a main interaction. On the right side is mainly for like user study. It's highlight the target, for example, that in this turbo model, you want to look for a very small, you want to look for that object, like the highlight at the red object, and but we want to give user better, because we did the user study for this application for normal user, not real like Boeing engineer. That's why they don't really know like very well about the structure. That's why we give three different direction of views, saying they will generally know where the position of the object you're looking for, and also a little shape of the object. And on the left side, it's like basic interaction. You can like rotate, tilt, and zooming. So the detail of the technique is we have this little probe. We call red sphere. We call it probe, and how it does is that when it comes close to the model, it expands its sphere collider, then covers the whole object, whole models. Then it explodes the first layer of the object, because when the object is loaded in the system, it's sort of like categorized into different layers based on the scale. Like large object, like at this case, for example, on the first image, say there are 4 objects exploded. The rest of the object remain static. So that is what we call first layer. It exploded. Then you search for the target object you want to look for. If it's not, then you go to the next layer, and the first layer will disappear. Then to the like last layer, where all the object exploded. And if through this process, you find the one you're looking for. So we did user study for this technique, and we developed another very easy method. We call it hole explosion. So what it does is that it explodes all the object at one time, and this is very simple. Very simple process, and we want to compare this to this process with our method, and we did a study design, two different methods, SBET versus WE, and two independent variable categorized in each for 3 categories. Like we evaluate the target size. We limit the threshold on the how detailed and how many pieces can render on a normal tablet, which is the second one is model complexity. So we set the threshold for the highest for 450 parts, and the second is 300, and the small model is 150 parts. And we did a user study for 36 participants, and each participant did 9 tasks with combination between different target size and different model complexity. Here's a study result. So from this table, we can see that between these 2 methods, the task finishing time and versus target size showing significant effect, meaning as the target gets smaller, or it impacts more on the results on the task finishing time. And For model complexity, it is the same. And for number of round targets, master, here, this one is we most focus on, number of round targets. For example, if they select target and they might think this is the right target, so they click it, we record that part, and they record it as an arrow. So like number of round targets is pose significant effect for method, which means for these two methods, WE and SPET, number of round targets really matters. Here's an interaction effect, which, repeat the one I just said. It's as the target size get, like at the target size 1 and 2 means not very small, but it didn't show too much the difference between two methods. When it comes to target size 3, it means the target size is really small. And then our method, SPET, like show some improvements here. So average number of round target selection for the X, the X is a complexity of models, and the Y is a number of round targets. So for skill-based exploring technique combined with size 1 target, SPET1, that's what it stands for. So like as the model get complex, people tend to make more mistake, which is understandable. However, for W, it shows significant effect on the method when it comes to round target selection for WE, as we suspected, because for 450 pieces of model pieces, if you explode it all once, there are sort of visual clutter on the screen, so it's really hard to find the one you're looking for. After that, we did questionnaire interview. First of all, questionnaire and then interview. So for 9, like very basic question related regarding these two methods. So interesting finding is, so 26 of participants using WE thought the interface of application was not easy to use. No participant believing that SPET interface is hard to use. And for finding small objects, fewer participants thought SPET was hard to use for finding small target than in WE. A lot of people think that method is a little difficult to find the target, especially when it comes to small target. So interview, I've just listed some questions here. For example, when they evaluate the overall impression between two techniques, they're saying 85% of participants using SPET said it was very good, compared to the 60 of the participants using WE. So conclusion, every time of finishing the same task between two techniques didn't vary significantly. But SPET performed significantly better for eliminating the number of round target selection. I think this could be very crucial if mechanics want to perform another operation right after they select the right target. For example, they select the stuff and they want to look at the parameter is what, and they want to replace it. So I guess like eventually it will save some times. So that's, we suggest that reducing the error rate will in fact reduce the total usage time. Of course, it's just very early stage of this technique, and there are some limitation because the the interaction is mostly based on the location of each parts of the model. So if like two parts, the central location, we see abstract location is the same, then it's really hard to separate them. Like the probe will push them together. And also similar objects, if like the target object is similar, there are like 100 the same object, because like crew, there are a lot of similar objects, so that could be a problem. And object with some color. Also object in dense environments, model complexity, and the relationship between components. All right, that's all. Thank you.